Hello again. Thanks for joining us. This is Space Nuts. Stop laughing at me, Fred. My name is Andrew Dunkley, your host. It's great to have your company on this edition, episode 343. Coming up, we're going to talk about some Australian physicists. Didn't know we had any. They've been looking into when carbon started forming in the universe, which was a couple of weeks ago, I believe. And there's a lonely galaxy that shouldn't be alone. Why? Well, it's got something to do with cannibalism. And we'll be dealing with some audience questions. We've had a couple of questions pop up this week about quantum entanglement. So we'll be tangling all that up and unraveling it and merging black holes. Not anything to do with the fact that it happens, but why does it happen? People want to know. Well, one person does. Nobody else really cares. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as always, is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How have you been
I'm
this past week?
Quite well, thanks. It's my grandson's birthday today. He's 8, and his name is Nate. And today is going to be great, and I won't be late for his party. Same joke I told on the radio this morning. He actually heard it. I didn't think he even listened.
No, there you go. Oh, that's great.
And his birthday,
Nate.
by the way, his birthday is 15/3/15. He was born
there you
of
go.
March 2015. And my youngest son was born 9797. So we've got some interesting numbers in our
Interesting numbers. Yes, yes, indeed there are.
15/3/15. Pretty good. And how are you?
Oh, well, thank you.
Yeah.
Very well, thanks.
Yeah.
I had a nice encounter with our good friend David Astle on Sunday evening on the radio, which was
Wonderful.
Slightly unexpected, but nice to have. He, as always, was very complimentary about Space Nuts. So,
That's a nice
shout
change,
out to,
isn't it? Yeah.
shout out to David from Andrew and myself.
Yeah. Hi, Dave. That's terrific. Now, we might as well get straight into the guts of the program, Fred.
Not much else to do, really, is there?
No. I was going to make some coffee and maybe have a biscuit, but I'll do that later.
Yeah, a bit later.
Australian astrophysicists. I didn't know we had any, but we might have one or two. They've been looking into how carbon started forming in the universe. Now, this is very important because we're a carbon-based life form, are we not?
We are, yes. We're made of organic molecules, which are molecules that contain carbon. So it is important. And this is a really interesting piece of work. The lead author is Rebecca Davis, who is at Swinburne University of Technology in Melbourne. It's a fairly large collaboration that has done this work, but she's the lead author on the paper. And it's all about probing the evolution of carbon in the universe. And as you've just highlighted, carbon is very important. So it's nice to know where it came from. And we do know where it came from. We know that it came from the nuclear processes in stars, because that's where all the elements come from, with the exception of hydrogen and some helium and some small amounts of other stuff like lithium. These elements, they were formed in the Big Bang. But all the rest, which we often call the heavy elements, but astronomers peculiarly, and I think we've talked about this before, refer to them as metals. Yeah. Anything that's not hydrogen or helium is a metal.
Oh, oxygen is a metal?
Yeah. In the world of astronomy it is, that's right.
That explains the heavy breathing.
I love it. I love it. You should be on the radio, Andy.
I should.
I just picked up the wrong story here.
Yeah. Well, while you're looking for it, I read a story today about a radio presenter who's just broken the Guinness World Record for the longest time on air in a career. She started in, I can't remember, but she's from Texas, and she's just racked up like near 73, 74 years as a radio presenter. Started at the age of 12. So to catch up with her, I've got to keep going until I'm into my 90s. Which is only a couple of weeks away.
I was going to say you don't have long to wait. That's all right. Anyway, that's another story. So, Dr. Rebecca Davis and her colleagues, what they've done is, how do you probe the evolution of something like carbon in the universe? And the trick is to observe very distant bright objects. And the particular bright objects that they observed were quasars. Quasars are almost like beacons in space. They were very common in the early universe. They are basically the result of black holes in the centers of galaxies, young galaxies, gobbling up lots of material and emitting lots of radiation. So quasars are detectable over vast cosmic distances. So when you look at, quasars perhaps at distances of 12 or 13 billion light years, you're looking back in time by that amount. But what you find is the light of the quasar on its journey to us in the present time, as it has made its way through space, passes through basically the gassy environment of the universe, the intergalactic gas within the universe. And that gas imprints on the light what it's made of. And it's such a brilliant trick because this is all about redshift. So this imprint from different distances looking back in time gets stamped on the spectrum of a quasar at different places, which you can immediately identify as being a different era back in the past. And so what they've done, I saw that.
Yeah, I've just in my head.
It's a very neat trick. It gives you this handle on essentially the way things have changed over cosmic time.
Yeah.
So what they've done is they've looked at the signature of carbon over very long periods, and they've found that in the early universe there was a lot of cold carbon, which was sort of replaced as the universe evolved by warm carbon. Now, you might well ask, Andrew, how can you tell the difference between the two? Well, I'm really glad you asked me that, because it's all about what we call the ionization state of the carbon, how many electrons it's lost because of temperature.
Yep.
And so I think if I've got this working out in my head properly, the warm carbon is carbon 4. That's an ionization level of 4, lost 4 electrons, something like that. And the cold carbon is carbon 2. And there was more carbon 2 in the early universe than later on. So the question is, why is it so? And there are two.
Julius Sumner Miller would have asked that question.
As he would have asked, that's right. Yeah, there's a name to conjure with. Yeah, I never knew him actually. No, and I arrived in Australia kind of after the Julius Sumner Miller era.
I just loved watching him on TV after school.
Yeah.
His science show. It was fantastic.
Yeah, I that's what everybody says, and I wish I'd been there to see it.
He was like a mad professor. He obviously got all your hair, Fred, because he's
had more
Einstein. An Einstein haircut.
Yeah. There was a fellow at the UN when I was there last month who looked like Einstein, and I kept wondering, is that Einstein?
Is he sitting next to Elvis?
Maybe he was. I did see Elvis. No, I didn't. Anyway, the two theories, and I'm going to quote here from Cosmos magazine, which has got this very succinct and way of putting it. I should credit the author, who is Efrem Yazgin. He is the author of this article on Cosmos magazine. What he says is two theories have been put forward to explain the increase of warm carbon. First is that carbon became more abundant purely because it was being formed through nuclear fusion in the young universe's stars. In other words, that first burst of star formation at the end of the universe's dark ages, when the first stars formed, maybe that's where it, what made it warm. What Rebecca Davis goes on to say is, during the period when the first stars and galaxies are forming, a lot of heavy elements are forming because we never had carbon before we had stars. Yeah. One possible reason for this rapid rise is just that we're seeing the products of the first generation of stars. But, and again, I'm quoting from the Cosmos article, that doesn't quite account for evidence in the study, which shows that cool carbon decreased in the same period. And that the suggestion is that this perhaps was meant there were two phases of carbon evolution, a rise when the first stars kicked in, followed by a plateau. And so that's essentially where the measurements led them to this this conundrum. Why do we find this drop in the amount of cold carbon compared with the amount of the drop in the amount of cold carbon compared with the amount of warm carbon? And the jury appears to be still out. I think there's a number of ideas. One of a nice quote from Rebecca Davis: "Our results are consistent with recent studies showing that the amount of neutral hydrogen, which is just cold hydrogen, in intergalactic space decreases rapidly around the same time." And a nice note looking to the future: this research also paves the way for future investigations with the Square Kilometre Array, which aims to directly detect emissions from neutral hydrogen during this key phase of the universe's history. So maybe it's not going to be until we've got the Square Kilometre Array later in the decade that we'll find out why this conundrum occurred with the carbon.
Wow, it is interesting though, and it's it's opened, I suppose, more questions as these discoveries tend to do, but there appears to be a smoking gun, I suppose.
Well, yes, since smoke is usually carbon, often carbon, that's probably right.
I'm sure.
Depends on what's burning.
Now, we are going out live on YouTube and Patreon. And have you got time for an off-the-cuff question from one of our listeners?
Yeah,
this
fabulous.
From a YouTuber called Ghost81. Quick question for Professor Watson. If you jump on the moon Miranda, you can jump 57 meters high. What happens when you land? Would it be slow, graceful, or an accelerating death dive? Good question.
It would be. You'd probably have the same impact, feeling as if you jumped on Earth.
Oh.
Because what you're doing is you're jumping as high as you can. You jump as high as you can on Earth, and you will land. You might strain. Certainly, if you were me, you'd strain your knees. I can tell you, I don't jump anymore. But it would be a soft landing, as it would be on Miranda. Okay. And it's because what you're talking about here is the acceleration due to gravity, which is much, much lower on a moon like that. So you get up to 57 meters, and you gracefully come back down again and land as though you were a ballet dancer finishing a pirouette.
Okay. I mean, if you jump from 57 meters on Earth, you'd probably go splat.
You would go splat.
But on Miranda, you'd probably land reasonably safely.
Yep, you'd land like you would if you were jumping as high as you possibly could here on Earth.
Okay. Fair point.
All right. Except more slowly.
It's all relative.
Lovely question.
Lovely question. Thanks for the question. Lovely to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Yes, indeed. And we continue with our next topic, and it's a lonely galaxy. Lots of songs have been written about this poor fellow. But this is a galaxy that's far, far away and should not be by itself. That's what's weird about this story. So what's happening here, Fred?
Probably, as you alluded to at the beginning, a case of extreme galactic cannibalism. But the story is more complicated than that, and it's quite a nice story. I love the headline on Science Alert: "This distant galaxy is all alone in space because it ate its friends." That sums it up.
I like the name of the author, Michelle Starr. What a great name for.
Oh yeah, Michelle's a classic. That's right. She. I had a colleague, many colleagues who've got names associated with astronomy. Peter Starr used to run the Warrnambool Observatory on the Cannibal, and one of my favourites is a colleague from the Royal Observatory in Edinburgh, or the University of Edinburgh, as he was, Alan Heavens.
Oh, wow.
That was very appropriate.
I still can't get past one of the best names in a job that I've ever heard. It's an Australian meteorologist, works for the Bureau of Meteorology. Her name was Gina Weatherhead.
Oh, yeah.
I'm not kidding.
Classic.
Used to do radio reports. Gina
Yeah.
Wesley. I think she got married, so I don't know if she kept it. I would have kept it.
Nominative determinism is what it's called, isn't it? It's where your name determines what you do.
Yeah. All right. Well, I'm just clearing in a bunch of trees, apparently. That's what it
Yes, you are,
actually
that's
is.
right. And I'm just the son of what? So there you go.
Yeah.
Anyway, back to this story about this hungry galaxy. And one of the things I like about this is this particular galaxy has the elegant name of 3C297. And the 3C in front of it tells you that it's what it is. It's the 297th galaxy in the third catalogue of Cambridge, or the third Cambridge catalogue of radio sources, which dates back to the 1960s. It might even be the 50s, actually, when this catalogue was being prepared. It could be the 50s. So this is a galaxy that has been observed for a very long time. It's a very bright galaxy. And in fact, it's, again, we talked about quasars in our last story. It's effectively a quasar. It's radio loud. That's why it's in the radio catalog, the third Cambridge catalogue of radio sources. But it also emits visible light. So the quasar is basically the black hole at the centre of this object. That's a supermassive black hole. It's scoffing material so quickly that it absolutely beams out light. And quasars are the brightest objects in the universe, at least in terms of the fact that they keep on shining continuously.
Yeah.
So, what's odd about this galaxy? Well, it is a galaxy that you would normally associate with a large cluster of galaxies. And how do you know that it would be in a cluster? Well, galaxies of this size seldom come alone. And a galaxy in a large cluster is usually surrounded by basically high temperature gas. And that high temperature gas is there around 3C297. It's been observed by the Chandra X-ray Observatory, a space telescope that looks at high energy radiation. And so there is the detection of this high energy gas, high temperature gas around this lonely galaxy. And that's the bit where it's a misfit, because normally with that high temperature gas around it, it would be part of a large cluster, and there'll be several galaxies of its size in the middle of that cluster. There's other evidence as well that came from Chandra that it's within a huge cloud of gas, because some of the jets of material that are being squirted out of the black hole are actually bent because they've hit the flow of the interstellar gas. One of them has illuminated a bright spot of interstellar gas that's I think it's 140,000 light years away from the galaxy itself. The beam of radiation coming from the black hole has hit this other cloud of gas, and once again, it's emitting X-rays. So all the evidence is there, suggesting this lonely galaxy sits in a giant gas cloud that would normally be populated by other galaxies. Now, Andrew, there's a twist to the story here,
Right.
because when you look at it in big telescopes, you can see that it's surrounded by other galaxies. Except, sorry, say again.
Infrared?
They probably are infrared, actually, the observations that have been made, because this thing's at a distance of 9.2 billion light years. So its light has been well redshifted. But the answer here, and the twist in the story, is that the astronomers who I haven't mentioned in this story, I think it's led from the University of Torino in Italy by Valentina Misaglia, and actually there's a nice quote from Valentina. She says, "It seems that we have a galaxy cluster that is missing all of its galaxies. We expected to see at least a dozen galaxies about the size of the Milky Way, yet we see only one."
Wow.
Which is kind of what I just said. But the reason so what I said was, yes, there are there are other galaxies around it, but what Valentina and her collaborators did was went to the Gemini Observatory on Mauna Kea in Hawaii, which has two 10-meter class telescopes, and used a spectrograph to measure the redshift and hence the distance of these other galaxies. There are 19 of them surrounding 3C297, and it turns out that all of those other galaxies are at different distances from 3C297. So they're just line of sight coincidences. They are not anywhere near 3C297. And so they're not the missing galaxies in this cluster. And so that galaxy is really all alone. And what they are, what they've determined from these observations, that this is an object which is usually called, I think it's called a fossil cluster. I think that's how they describe them.
Yeah.
And a fossil cluster is one that was once a cluster of galaxies, but one galaxy has had such a powerful gravitational pull that it's gobbled up all the other ones, which have now become part of that one central galaxy. So it is, this is the outcome of this research. Actually, I think the normal term is a fossil group rather than the fossil cluster. But
Right, yeah,
you get the drift.
You, me, and Hugh make up a fossil cluster.
I guess we do. Yes, that's right. Cluster of fossils. Well, there you go.
Keep them out of it, though.
When's Hugh going to get really annoyed with you, Andrew? That's what I want to know.
That happened years ago when he became boss at the ABC. So, pretty sure.
Oh dear, that's the good thing about fossils. They don't tend to get annoyed that much.
No.
But there's still there is another aspect to the story that makes this a kind of record breaker, because this is, as I said, it's a look back time of 9.2 billion years.
Yeah.
And it's actually the earliest fossil group or fossil cluster that astronomers have found. Because it was thought that these sorts of events, galaxies gobbling up their partners and friends, only happened relatively recently in the universe. But this shows that it actually occurs much earlier in the universe than astronomers have thought.
Mm. How big is it, did you say?
Big. It's about the size of the Milky Way, I think.
Yeah. So does that suggest that before all this started, it was much smaller, or?
Yeah, yes, that's right. That it would have been a more modest galaxy. It may even be bigger than the Milky Way, around the size of the Andromeda galaxy.
So, what would have given it the power to be the dominant in that area?
It's a great question. Probably, it would have started off it would have been surrounded by probably 100 satellite galaxies. We think that that's one of the consequences of galaxy formation, that you quite often get a big spiral with lots of satellites around it.
Yeah.
And the big spiral begins by eating them all up. And that's what's happening with the Milky Way. It's gobbling up the two Magellanic Clouds. They're being disrupted tidally and will form part of the halo of our galaxy in a few 100 million years. But that's just the start of the process. And then if you've got other smaller galaxies, and I guess the analog in our local group of galaxies is our own galaxy in Andromeda, which are whizzing towards each other at, 300 kilometers per second. I think it is something like that. Andromeda is a bigger galaxy than ours. And what will wind up when this collision occurs in 3 or 4 billion years is there will be a combination of the Milky Way and Andromeda, which is already being called I think it's Milkomeda, and it's usually called something like that.
It's horrible. It's
horrible. Yeah, it is horrible. Yeah. But that will be a single galaxy, and then it'll probably gobble up. There's another galaxy called M33, which is another spiral galaxy, smaller than both the Milky Way and Andromeda, and that'll probably get sucked in as well.
Yeah.
So I think, are already seeing the start of our galaxy becoming part of a fossil group. But remember, where the universe is now 13.8 billion years old, and that's the time that you kind of expect these things to be happening, like now, whereas this one occurred 9.2 billion years ago. So it is quite an interesting observation.
Yeah. Milkometer. I guess is it better than flipping it over and becoming Amway, which I think doesn't work.
I don't think that works. I don't know. I think milkometers. It's a bit more pure than Amway, I think.
Oh dear. Yeah.
Yeah.
I wonder if it's skim or what you get a skimming going on, I suppose.
Scometer might do it.
Oh,
No, that's no.
that's horrible too.
Full creamometer. No.
But, the thing about this lonely galaxy is that it's not going to be the only lonely galaxy in the far distant future, because we'll all become lonely galaxies.
Yes, that's right. That's exactly right. We're all on the way to it.
Yeah, which will be rather sad.
Right.
But I don't know if we'll be around to see that, because who knows what the future holds. But yeah, a fascinating story. And if you do want to have a read of that, it's on the sciencealert.com website, sciencealert.com. Yeah, you can chase it up there. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Guess what, Fred?
Question time.
Question time.
Hey, look, I'm on fire
Although
today.
we've already done one, but that was from a live studio audience. We're going to do 3 questions today, but 2 of them basically ask similar things about quantum entanglement. So I think the best way to play this would be to tackle them one at a time. So the first question comes from Evan.
Hi, Andrew and Professor Watson. Evan Carlo here from Newcastle, Australia. My question is related to quantum entanglement. Suppose we have a set of quantum entangled coins in 2 black boxes, one spinning clockwise and the other spinning counterclockwise. Fred has one of the boxes here on Earth. Andrew gets a ticket on a rocket to Mars and brings one of the boxes with him. Will the entanglement collapse as soon as either Fred or Andrew open their box and look at one of the coins? If so, is that message somehow going faster than the speed of light? Given at quickest, it takes 3 minutes for light to go between Earth and Mars. Oof, my brain hurts. Love your podcast, Jans. Keep it up. Good stuff.
Evan, I think your brain hurts because the supercars were in Newcastle last weekend, and they're pretty darn loud, those V8s. It was nice to see. I come from Maitland, which is only half an hour's drive up the road from Newcastle, so I know Newcastle well. It's a beautiful city too, absolutely glorious.
I was there at the weekend.
Were you?
Yeah, it was.
Not a nice place.
Not for the supercars, but one of my sons lives there, William.
Oh, okay. Did you hear
Will lives there?
You should have.
No, but I heard the jets from Williamtown flying over the supercars.
Yeah.
And in fact, saw one of them as we were getting on the train. We went up by train,
Yes. Well, it's easy by train to get there.
It is. It's nice.
It's 6 hours to get to Sydney by train from where I am. That's only because every time it hits a hill, we have to get out and push. But yeah, quantum entanglement coins. So you've got the clockwise one in your box on Earth, and I've got the anti-clockwise one in my box, and then I go to Mars. What happens?
Well, it's exactly what Evan says. But it is. I mean, it's an interesting aspect. Because the real physicists, not people like me, don't see entanglement as basically contradicting the speed limit of the universe, which is the speed limit of the speed of light. Because what they're saying is that entanglement it's sort of preordained by the entanglement itself as to what your coin's going to look like when you look at it. So the deconvolution bit is when it stops being a quantum object, and that's when I look at mine, it stops being a quantum object. But you can look at yours at any time, and you will find that the spin's in the opposite direction, because that's the way it was when the two were created, if you see what I mean. It's not that a message is being sent saying, "Hey, Fred's looked in his box," because you've got to look in your box too to know that it's quantum entangled. I can tell by the expression on your face that I'm digging myself deeper into the hole.
I thought Evan's headache.
Yeah, it gives me a headache as well, Evan. It is a strange and wondrous phenomenon, which I think we clearly don't understand it properly, although the quantum physicists are quite comfortable with it, and they are using it. Entanglement's being used as, in cryptography and things of that sort. So,
I think they sit in their canteen and when they make their tea, one of them stirs it clockwise and the other stirs it anti-clockwise.
It could be right.
That's probably what happens. But I'm none the wiser after that, to be honest.
No, I don't think Evan will be either. Maybe I should lift my game, really, shouldn't I? I should look at the equations and find out what they tell us.
If you could figure it out, you'd probably win a Nobel Prize, wouldn't you?
Yeah, that'd be good.
Yeah.
That'd be really good.
Yeah. There's room on my trophy cabinet for one.
Yes. We'd definitely share it, Andrew.
Yes.
Would have to be shared.
It
would probably be an entangled Nobel Prize as well.
Maybe, yes. Thank you, Evan. And sorry, couldn't answer it, but we're going to get even more confused now because David is also asking a sort of a combo question about light and quantum entanglement.
Hey guys, my name's David. I'm from Saskatoon, Saskatchewan in Canada. I want to say, first of all, thanks for the podcast. I'm new to the whole science, space, universe, or multiverse, I guess. And I've been learning a bunch through your guys' podcast, so thank you for that. I have a couple questions. First question was, I believe it was in January of 2022, where scientists shot a bunch of light at each other, and the energy output was more than the input. Would this in any way tie into the theory of black holes, white holes, in the sense that black holes consume a bunch of energy, including light, and the output is more than the input in the sense that it creates the entire universe through the white hole? Maybe that's a stupid question. Let me know. And secondly, staying on the subject of black holes, if one of two particles that are quantumly entangled enter a black hole, would they still be quantumly entangled? Or I guess what kind of happens to that? Once again, thanks again for the podcast, guys, and look forward to hearing the answers.
Wow. Thanks, David. They were deep questions. I do remember hearing about that experiment where they pointed light at each other and the output was higher than the input, but I can't remember the details. Have you heard of anything like that, Fred?
Oh, yeah. In fact, we talked about it.
I thought we did. See how good my memory is?
Yeah. So it's sorry, I'm just reading something here. It's the fusion reaction, which was it Lawrence Livermore lab, I think. So they actually generated a fusion reaction for the first time that yielded more energy than was put into it. Now, this is the kind of holy grail of energy production. If we can bring about nuclear fusion and control it, then it's a clean source of energy that's almost infinite, not quite infinite, but it's what powers the sun. This transition of making hydrogen atoms into helium atoms and reaping the slight percentage of mass loss that there is in that reaction that turns into energy, and it turns because the m for mass is multiplied by the speed of light squared, as in E equals mc squared. You've got huge amounts of energy coming out. The problem is sustaining the temperatures that you need to make that work, and so the promise of nuclear energy from nuclear fusion is still, as it has been for many years, probably 50 years away. But this was the first time that with all the experimental controls and everything, you can guarantee that that fusion has taken place and that you have generated more energy, only briefly, but you generated more energy than you put in. So it's a milestone. I was talking, interestingly, to nuclear physicists when I was at the UN back in February, because I sat in on some meetings about nuclear power sources in space, which were really interesting.
Yeah.
And there was certainly a feeling among those physicists that the Lawrence Livermore Laboratory, if I'm correct in saying that's where this work was done, was really, milking the hype as much as they could for this event, and were, I think, getting these people felt they were getting more vibes out of it than possibly they should have done, because they said this was entirely expected, that if you clout these two lasers together or laser beams together at high enough energies, then you're going to get nuclear fusion. But I think the world, they did agree that it's still a milestone.
Wow.
So just to sort of close the loop on it, there is a giant European experiment going on in the south of France called ITER, and I can't remember what ITER stands for, ITER, and it's about sustained fusion reactions. That machine has been being built for a very long time. Probably more than a decade ago, I actually talked to one of the physicists working there, who was a strange and interesting person. But that will probably eventually generate a fusion power, or demonstrate that fusion power is possible. But then the step to build power stations using this is probably half a century away.
Yeah, but
so
it's good to know it can happen. It's great to know that can happen.
Yeah.
And the other little leap forward that was announced last week from Monash University in Melbourne, Australia, was that Australian scientists have discovered an enzyme that can convert air into energy.
Oh, yeah, that's right. Yeah.
This is fabulous. And they've published their findings in the journal Nature. But basically, if they can harness this, it will lead to, mobile phone batteries being able to charge themselves from thin air, things like that. And they even think that the technology could grow to the size of batteries required for electric cars and things like that. It will probably take a long time, but then they're talking not 50 years, but 5 to 10 years before this technology is rolled out. Yeah. So that's really exciting. And if you want to, that's worth reading, that story. It's at phys.org. Now, I've got a caveat here. It's phys.org. Confused a few people by saying phys.org because they think it's FIZZ. And or double Z, sorry, for you Americans. But phys.org, phys.org that's what I mean when I say that. But that's a really exciting discovery, Fred.
Yes, that's right. It is. It's a milestone.
So the second part of his question,
David's question, By the way, David,
quantumly tangled particles entering a black hole, will they stay entangled?
I suppose what we mean by entering the black hole is crossing the event horizon, because that's the bit where, I don't know the answer to this. And I'm just trying to think. I mean, as Hawking radiation comes about because of virtual particles springing into existence at the event horizon, and one goes in and the other comes out. So they turn into real particles. I honestly don't know what would happen to entangled black particles entering a black hole. No. I will try and find out for you, David. I'm coming to Canada next year, actually, so maybe I'll, talk about it then.
I'll be there in May this year.
Yeah, of course you are. Yeah, you're heading there in May.
3 years late.
Let's just kind of put a bit of a lid on entanglement, though, and all these mysteries, because what I'd like to do is refer everyone to a Scientific American article which appeared. Actually, it's just appeared. It's appeared only this week, February 13th, 2023, which is headlined, and this echoes what I was saying earlier. Quantum entanglement isn't all that spooky after all. And what the author of this, whose name is Chris Ferry, says is the way we teach quantum theory conveys a spookiness that isn't actually there. And I would I would actually recommend all our listeners who are interested in quantum entanglement to read that, because it is, it is always less spooky than what we convey it. It's a really interesting phenomenon, but it doesn't break the speed limit of the universe. That's the bottom line.
Okay. Again, sorry, David, can't answer your question, but it's
Read
quantum
the article.
entanglement, and Fred hasn't got the right packet of cornflakes yet to get his particle physics certificate so that he can answer the question. So he's got to keep buying cereal until it turns up. You remember that old joke? He got his driver's license from a cornflakes packet?
Yes.
Particle physics.
I think my dad did, actually.
Dear, oh dear. Thank you, David. One more quick question, and it's an easy one. It's all about black holes. This is from Duncan.
Hello, this is Duncan here from Weymouth in Dorset in the UK. Quick question. Can you explain in layman's terms, please, how black holes merge? That is to say, if nothing can escape from a black hole, when two black holes come together, how do they interact? Surely they would literally just roll around each other, because neither one could allow anything to escape from the other to merge them into one whole. There probably is a simple answer, but I can't think of it, because nothing can get out of a black hole. Therefore, how can they possibly join together into one big one? Because they would just wrap around each other. Maybe you could explain that for me. Keep up the good work. Glad that you're back. Missed you over Christmas. So, anyway, thanks for the answer. Bye.
Bye. Thanks, Duncan. Stop making trouble for yourself. Such an easy question. But I see the logic of his thinking.
Yes, I do
if
too.
nothing can get out, how can they get together?
Well, the bottom line is nothing can get out, but stuff can get in.
Yeah. Well, it comes down to which one's the bigger black hole, doesn't it?
Yeah. So when you look at, the classics studies of merging black holes have come from LIGO, from the Laser Interferometer Gravitational Wave Observatory in the USA, when they made, in fact, the first gravitational wave observation that was made, that was verified, was in 2015. Or I think it was released in 2016, but for an event that occurred in 2015. In fact, on Marnie's birthday, the 14th of September. That's why I remember it. And it was two black holes merging. Yeah. And so the gravitational waves that emitted fitted the theory perfectly. And the theory says that you'll get exactly as Duncan has suggested, that these two black holes will spin around one another in ever increasing speed, getting relativistic, that's to say, getting near the speed of light, getting ever closer to one another. And then basically they just merge. They do merge. They're not, they're not constricted from merging by the fact that they're black holes. They are gravitationally attractive. Each one is attracted to the other with an enormous force. So if you think of them as singularities, they don't have any dimensions, then they basically just add together with a colossal release of energy, which is why their masses don't necessarily add up. So it's not that much of a conundrum. The one thing that is released is gravitational energy, and that comes about because they're gravitationally highly attractive bodies. There's not really that much to add. There's what they were referring to in the LIGO results was I think it's called a ring down, which is the last bit. It's the phenomenon where the black holes themselves merge. But I should check that. I think it was called a ring down. Might be worth just having a look at that, Duncan, online, black hole ring down, and see what it comes up with, because that will tell you about the instant at which these black holes merge.
I'd caution you, Duncan, that search could take...
Well, maybe so, yeah. Maybe astrophysics might be in the search path there somewhere.
Definitely a good idea. Not that I've ever tried it, but
No.
it's certainly a search pattern that could take you to the wrong place.
Oh, yeah, that's right. You never know where you're going to wind up, do you?
You don't, do you? The internet's a lottery.
It is sometimes.
Especially if you look at FIZZ.org. I don't know where that takes you.
Yes, that's right.
Annoying.
Anyway, it's a great question, Duncan. I hope all is well down there in Weymouth. I'm sure it is. I suppose it's up there from down here.
It is up there. Then again, I maintain that the universe is upside down, which puts us on top. So,
well, yes,
that's my
probably
theory.
True. Yeah.
All right, Duncan, thank you. Lovely to hear from you. Thank you to everybody who sent in questions. We've got a whole bunch of others to go through, which we'll tackle over coming episodes. But if you do have a question for us, go to our website and send it to us. You can do that by going to spacenutspodcast.com or spacenuts.io. Now, if you click on the AMA link, which I'm doing right now, it will take you to a page that says be a part of the show. Leave an audio question for Andrew and Fred and have it answered in the Q&A segment of the podcast. And you can simply send us a text form question by filling out the form, or you can hit the record button and away you go. Or if you want to just do it the easy way without having to click on another page, just click on the send us your voice message on the right-hand side and it will do just that. Don't forget to tell us who you are and where you're from. And while you're on our website, have a look around, find out about becoming a patron. Go to the Space Nuts shop. You can get the latest news from the Astronomy Daily newsletter and so much more at spacenutspodcast.com or spacenuts.io. We spent millions of dollars to own both of those URLs. So, yeah, that's where the big bucks go, just so we can keep our website alive. We're finished, Fred. Thank you so much.
Thank you, Andrew. Thanks for bearing with those half-baked explanations about entanglement.
We strive for adequacy as always. And it's good to know we sometimes achieve it. But,
no problem.
Nice
good
to catch
talk.
up, Fred. We'll catch you next week.
See you later.
Okay, bye-bye. Fred Watson, astronomer at large, and thanks to Hugh in the studio who is stirring his tea and pushing a couple of buttons on his phone because he doesn't know how to use it yet. Technology, you know. And from me, Andrew Dunkley, thanks for listening. Looking forward to your company on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.